So thank you everybody for coming to the second lecture from Professor Randall Wright. You can take over, Randy. I'll stop sharing.
Very good. I will start sharing. Hello, everybody. Can you see my screen now?
Yes, it's not full screen though.
Sure it is.
Yeah, now it is. Thanks.
Okay, very good. So everybody, we were talking about search theoretic models of the exchange process as a way to think about modeling carefully frictions, including information, etc. And then we could think about institutions that might arise to ameliorate those frictions, such as money, or more generally, assets serving as payment instruments. And if we had time, we'd talk about banking and a lot more details about credit. But we're probably going to talk mostly about money today because we don't have that much time. But I encourage you to consider using this class of models to talk about other institutions, like in particular banking, alternative credit arrangements, etc. What we're going to do today is generalize the class of models we did last time, instead of assuming M is in 0, 1. So we'll generalize that, and there's different ways you can go. You can assume M is still integer valued, but allows for more general inventories in 0 or 1. It's kind of a natural approach. You might think it's even good for computational work because the discrete state space is something the computer can handle. Or you might go all the way to divisible money. In either of these cases, you could put an upper bound. The way some of these people proceed is to put an upper bound, but assume it's sufficiently big that it's typically not binding or binding with a low probability. In general, the hard part of this entire approach is how to handle the distribution of assets or liquidity across agents. And there's basically two approaches: computational work, which I'll just touch on today, and then some theoretical devices by various people. Now, computation is wonderful. In macro, many of the issues are quantitative, so going to the computer is where you want to be in the longer run. But for monetary issues, you don't want to go to the computer too quickly because some of the conceptual issues include things like existence, which is hard to prove on a computer, although you might hope you find something that's at least an approximate equilibrium. Uniqueness, which is difficult on the computer as well, because maybe you only find one or two, but there could be lots of other equilibria that the computer is not good at finding, or you're not good at telling the computer how to find. And dynamics are very hard on the computer. Stationary equilibria are relatively hard. Dynamics are hard, and we're interested in dynamics. So we're going to talk mainly about, of these different classes of models, the one that Lagos and I developed. And it's nice because I think it's realistic, tractable, and easy to integrate with standard macro or GE, whereas pure search models are not. So it's even the basic Pissarides model of the labor market, it's pretty hard to put that in general equilibrium. Although the same tricks, or let me call them devices, I'll show you today, can be used for that purpose. And I'll talk more about these attributes or assets that this approach has in a few minutes. Let me first show you some of the issues. So here's what Miguel Maliko did about 15 years ago. He's now at the Bank of Canada. And when he was doing this, it was really pushing the bounds of computational economics pretty far. So suppose we take exactly the same framework, but allow you to have any money holdings in zero infinity, any non-negative number. Well, this value function looks a bit oppressive, but it's actually very intuitive. So there's some probability alpha 1, you're going to be in a meeting where you find yourself in a position to buy something, because it's that type of single coincidence. Now you're going to buy something, but the amount of goods you get will be, in general, dependent on the money holdings that you have and the money holdings of your counterparty. So already this raises an issue. I'm going to assume, as Maliko did, that these money holdings of both agents are observed. Not the most natural, but without that, it's hard to think about doing the bargaining. It could be done, and it's an interesting open question. It should be done, but it hasn't been done in this class of models, at least not to my satisfaction. There are some approaches which touch on that. So then you're going to have continuation value. You're going to spend some of your money, let's call it D. In general, it could be any real number, non-negative. It's also going to depend on your money holdings and the money holdings of your counterparty. And you have to take the expectation with respect to the cross-section distribution of assets. There's an alternative single coincidence meeting, where you're going to produce some amount and receive some money in exchange, or more generally assets. The amount you produce and the amount you receive in payment will depend on the money holdings, this time of the counterparty and yourself, because my notation here is Q and D are the quantity of goods and money, more generally assets, when the buyer has M and the seller has M hat. So in the first meeting, you're the buyer, your money holdings come first. In the second type of meeting, you're the seller, your money holdings come second. And there's some probability you won't trade. I could put barter in there or make it a real asset, but I'm not going to do that right now. I'm not going to stick with this model too long. I just want to show you how it works. And, you know, I simplified it on the next slide because these terms in curly brackets here are just almost the surpluses of trade. It's the actual value, instantaneous utility plus continuation value. If I subtract off the status quo payoff, or the outside option, you get the surplus. I wrote it this way because on the next page, I want to show you something which requires easier notation. I want to show you the bargaining problem. And
Sorry, before you move on.
What's that?
Before you move on to the question.
Yeah, question.
Yeah. So when I go to Walmart and I buy something, or I go to Target, or I trade with somebody, it doesn't really, I don't really ask them like how much total money holdings they have, right, before we conduct the trade. So why is it formalized this way? That you need to know.
Basically for simplicity. As I say, it'd be very useful to push this forward and try to do it where you don't observe the money holdings of the counterparty. Now it's a little bit tricky. You see, the buyer could potentially lie, but he can't lie in an upward direction. He can't go into Walmart and say, you know, give me $10,000 worth of whatever the good you want if you don't have the money. You got to be able to show the money to do the deal. It's more tricky to think about knowing the seller's asset position. Now, don't think only about you going to Walmart. Sometimes these models are used to talk about commercial banks trading reserves in the interbank market. There it may be more or maybe less problematic. But I don't want to dwell on it because I'm going to abandon this approach in about 3 slides. And you know, one of the reasons is right what you mentioned. It's not so natural to think you know the asset position of your counterparty. So we have, it's not that we don't have theories of bargaining under private information. It's more like we have too many. I suppose if I was going to push this direction, I would probably not use bargaining at all. I'd probably use something like price posting. It's true when you go to Walmart, you don't know how much, what their portfolio is. You also don't negotiate the prices typically. So I might replace it, and some people have done that. Papers by Green and Zhao. They use price posting instead of bargaining. So this, I would say, is simply the natural extension of what we did before, but it raises many issues, some of them computational and some of them conceptual, like the ones you just raised. Nonetheless, if I do make the assumption that it's common knowledge what money holdings both parties have, then you can use standard bargaining. So here's Nash, and that's the reason I defined those surpluses in the previous slide. You know, the Nash bargaining problem maximizes the surplus of one agent to some power multiplied by the surplus of the other. If you had private information like you were suggesting, and I was suggesting, well, you'd have to appeal to a whole different class of bargaining. In fact, Maliko uses take it or leave it offers, so that's theta equal 1, but in principle, other solution concepts could be used. And there's going to be some distribution of money holdings that's evolving over time. I want to define equilibrium here and then move away from this model. So the reason I want to do it, there's a wide class of models. Basically, any model with frictions is going to have some equilibrium that looks like this on many dimensions. Usually looks just about like this. There's some payoff, the value function. There's some actions, which here are the decentralized trades, quantity and assets, and some distribution. The value function solves the Bellman equation. That's actually kind of standard in dynamic programming. the Q and D solve the bargaining problem. That's kind of standard if we make the strong assumption, but the simplifying assumption that money holdings are observable, the bargaining is straightforward. And it's this G distribution that's kind of messy. I wrote down how it evolves for an individual, your money holdings next period. Well, you might not trade, so you stick with what you had. You might make a sale, so you raise your money. You might make a purchase, so you lower your money holdings. And these occur with certain probabilities, including the probability of meeting the right counterparty. Now, one should probably do this using measure theory, but I'm not going to bother. I'm just writing this out. G had a density.
Randy, Narek has a question.
Yes.
Hi, I'm Narek. I'm a third-year student at Princeton. I want to ask a question. Why is the state variable for the value function the money holdings instead of being the money holdings and the distribution of money?
It is the distribution of money. I just didn't put it in the notation. So when you're doing dynamic programming, sometimes you try to write down a relatively tractable state variable. So I've included the individual state, your own money holdings. I haven't included the G, but that should be in there. It's in there implicitly. In fact, this class of models is hard to compute, and I'll tell you why. If you look at stuff in most of computational macro, where they use techniques, say Crucell-Smith techniques, you'll notice that the individuals in the model do not care about the distribution per se. This Walrasian markets, all they care about are the prices. Now, you might say the prices depend on the distribution. That's true, but usually you can approximate that very well by a small number of moments. Often, all you need is the mean. So these Crucell-Smith techniques replace the distribution. They don't need the distribution for the individual problem because they're price takers, and the dependence of prices on the distribution is well approximated by a small number, like 1 of moments. In this class of models, it's very different. These aren't Walrasian markets. You're trading with counterparties, not just your budget line. So you need to know the distribution, not only because it influences prices, you need to know it because it influences the meetings you're going to have, the counterparties you're meeting. So it's a little bit difficult. You can't do a good approximation. This is a numerical result. You can't do a good approximation here by some small number of moments of the distribution. You have to work a little bit harder. I'm going to quickly skip over the results. So Maligo computes this. And, you know, when he first did it, like 15, 17 years ago in MATLAB, it took hours to converge. Now it takes, you can do it on your phone in seconds. And you can see the nice distribution, increase in concave in your money holdings. This is for stationary equilibria. So we're having the G self-replicating over time. It's more challenging, as I alluded to earlier, to do non-stationary analysis. And here's actually the distribution. This is his notation. I just cut and paste this from the published article. Lambda is let's say the density. And he does 2 things in the model. One, he talks about price dispersion, which is kind of interesting. Obviously, prices are dispersed here. First of all, let me define the price as the number of dollars traded divided by the quantity of goods traded, conditional on the money holdings of both people. And that's the price in that meeting. And there's a distribution of money holdings. So you get this distribution of prices. Here's the density of prices. And he, for example, lets the frictions get smaller and shows that the distribution of prices tends to collapse to something that has smaller and smaller variance. And the idea is there, as you let the frictions get smaller, you look more and more like a Walrasian market in the sense that there'll be something closer to the law of one price. Although, of course, payoffs and other observables are not Walrasian, even if you get a low dispersion in prices. And he also talks about monetary policy. Lump sum transfers of M turn out to be a good idea in this class of models. It's the idea we talked about before. You can run out of money or run low on money, if not literally run out. If you always spend half your money, you're never going to hit 0, but you're going to end up with such a low value of money holdings, you can't buy very much. So throwing in lump sum transfers is a kind of partial insurance arrangement for agents who are kind of tight on liquidity. You know, Ben Bernanke was pretty big on that. He was giving millions of dollars out to financial institutions and even wanted to do it for General Motors. That's good in terms of provision of liquidity. And this model doesn't have the funny property last time where when we change the money supply, you change the ratio of buyers to sellers. You don't do that here, right? Because everybody could be a buyer or a seller. As long as they have some money, they could be a buyer. The downside is people are going to not work as hard to get money if the government's giving it away for free. So you get this classic trade-off. Injecting liquidity is useful, but it provides bad incentives. And then the question is, will the optimal policy involve money creation and these lump sum transfers? The reason it provides bad incentives is it leads to inflation. If the government's giving money away to everybody, well, your money holdings are worth less, not worthless, but worth less. And that's why you're willing to produce less to get money. So it's the classic trade-off. And you know, lots more work could be done on this. I also want to go back to my example of commercial banks. You can have this as productive firms trading assets, entrepreneurs and capitalists trading technologies. You can do a variety of things here. And it's a classic scenario where you're trading off liquidity provision with inflation. Now, let me show you, I know I'm going very quickly over this. This is mostly like preview to show you what we're not going to do. Although, as I say, it's a fertile area for future research, especially with computation being so much faster these days. So here's what kind of is tricky. If you suppose you want a representative agent. Now, of course, you know, computational macro was mostly about non-representative agent models. They want some heterogeneity, typically in wealth or something else. But it's nice to have the neoclassical growth model or the real business cycle theory as a benchmark. So we kind of want to benchmark too, but we can't use, you know, the standard growth model because it's not going to have a role for money or liquidity more generally. So I'm going to show you how to get a representative agent version of this. And the big problem is, even if we start out with the representative agents, everybody has the same liquidity position. After one round of decentralized trades, some move up, some move down, some stay the same. In the next round of decentralized trade, this distribution fans out more. So you got to hope it settles down to some stationary distribution in the long run, and it does. That's the distribution Maleko finds. Douglas had this idea one day in the pub. He's my student from Penn. When I was teaching there, he hadn't worked on money before. He'd worked on labor search models. And he said to me in the pub, why don't you guys do this? After a round of decentralized trade, when the money distribution starts to fan out, his original suggestion was let people go to the bank. If they have less liquidity than they need, take some out. If they have more, put some in. And I immediately knew that's a good idea. However, at the time, putting a bank in seemed tricky. You know, banking is about multilateral trade, right? Banks intermediate between, say, savers and borrowers, and it entails a lot of record keeping. Whereas the building blocks of at least the early models in this literature had only bilateral arrangements in the spot trade, and it had no record keeping to make credit difficult. So I said, that's a great idea. But I made what's called a friendly amendment. I said, let's not use banking. Let's put in a centralized market. People who have more liquidity than they need, say more cash, they could consume more or take more leisure. Those who are tight on liquidity could consume less or work more and hence take less leisure. And maybe there's some hope that this distribution, which is fanned out a little bit after one round of trade, might collapse back down to a point. Indeed, if we start off with any distribution of liquidity, there's some hope in this centralized trading, the distribution may collapse to a point, and then we start every round of decentralized trade with a representative agent. That was the idea. Underlying the model is all the same frictions in terms of lack of commitment, and it's difficult to punish people if they misbehave because, record keeping or monitoring, those things are imperfect. And it's based on specialization, which generates the gains from trade that can't be fully exploited with direct barter. But there's some hope you can get a representative age inversion. Now, of course, let's explore this. So in discrete time, you can do continuous time versions of this, but to me, discrete time, I think, is more natural. It's going to be two sub-periods, a decentralized market, which looks exactly like the models we've been studying. In fact, it looks like Maliko's value function, although it's going to simplify dramatically. And then when that closes, you open up this centralized market, just like in standard general equilibrium. Now it's going to have a value function W. Remember W for Walrasian to keep your mind focused on which one is which. So, okay, let's see what happens. Let's set up this centralized market problem. And by the way, you could do it more generally. You can have several rounds of decentralized trade. So the distribution fans out a few times and then have them reconvene in a centralized market. You can do lots of generalizations. That's interesting, very interesting. In particular, Neil Wallace says he really wants models of money to have a distribution of money holdings across agents. And here you don't get that if you have only one round of decentralized trade. But if you have more than one round, you're still going to have a distribution. But every so often, agents get to go to the centralized market and rebalance their portfolio. Kind of like the old-fashioned monetary models of Baumol and Tobin, which were just decision theoretic models. They were not equilibrium models. They just told you how to manage your cash when you needed cash for reasons unspecified. But today I'm going to focus on one round of decentralized trade. So because we're macroeconomists, we know there's many ways to set up this centralized market with vectors of goods and firms, and just like in DeBrew. But let's do the simple version. We need two things to be good macroeconomists: consumption and labor. So here's my utility function from the instantaneous return of consuming some numeraire good, X, and with a time endowment of 1 and labor supply of L, 1 minus L is leisure. So what I'm going to do there is choose consumption, labor supply, and in general, a portfolio, but I think we're only going to have time for one asset models today. And it's a Walrasian budget equation, so there's no frictions here. Again, Leibniz's original idea was to introduce this simply as a way to harness the distribution of assets. But in fact, once you've got the centralized market up and running, you can add capital, then it looks like a real business cycle model. You can have vectors of goods, vectors of inputs. You can have different firms, then it looks GE. For today's presentation, I'll assume you can produce the numeraire good X 1-for-1 with labor, so the real wage is 1. So your budget constraint says your wage income fee is going to be the price of money in terms of the numeraire. So phi M is your wealth. You're going to take M hat out of the market for next period. And generally, you're going to have some taxes. Taxes are useful here because one way to introduce money is to have a negative tax and just print money and give it away. You can also contract the money supply by taxing people and withdrawing currency from circulation. So here's like a lemma, we'll call it the Lagos lemma. Suppose the utility function is in a certain class, then, and I'll tell you what class on the next slide, in the centralized market problem, which is kind of like an undergraduate micro problem, has something very convenient. First, history independence. Your demand for your portfolio demand is orthogonal to the portfolio with which you start the period. And second, your payoff is linear in general in wealth. With one asset, your only wealth is money and margin. This is useful, by the way, exactly because of, I'll come back to this later, but by way of preview, in this model, you're not going to need to know your counterparty's money holdings. Because in equilibrium, everybody has the same marginal value of liquidity. So these two results are extremely useful. You get what Lagos was hoping for. People will rebalance their portfolios, so they start the next round of decentralized trade with the degenerate distribution. Everybody's the same. I mean, conditional on your type. If agents are fundamentally different, like they have different preferences or different arrival rates or different anything, they're in general going to hold different amounts of money, but the money holdings that they choose will still be history independent. What's the class of utility functions? Well, we actually started with linear utility. We figured out it's easy to generalize it to quasi-linear. So as long as utility is linear in one of the variables, in this first case, leisure, in the second case, consumption, Russell-Long proved something which is useful. I should have known this, but I didn't. Any utility function like this, U11, U22 equals U12 squared, will also kick out a history independent portfolio demand. So that would include Cobb Douglas and CES, as long as the coefficients, basically as long as it's constant returns. So it certainly doesn't include any utility function, but there's a class of utility functions for which this works. A caveat, which I think means warning in Latin, it assumes interior solutions, at least in some periods. If you're at a corner solution, you get a little bit of a problem, but that's not too bad of a problem. So I can actually prove this easily. Let's do the simplest case, one I like the best. Utility is linear in labor or leisure, general and utility. What I've done here is I rewrote the centralized market problem, and now I'm going to eliminate labor supply from the budget equation, and I get this version of the problem, which makes it totally obvious that several things are true. One, your payoff is linear in your current money holdings. And two, your choice of a portfolio, which in the simplest cases, your choice of asset holdings, is independent of M. It depends on this cost of being liquid and the discounted future benefit. It does not depend on your wealth. That's the proof. An alternative proof is just use the general utility function, take the first order conditions from the problem, and then use comparative static techniques to take the derivative of M hat with respect to M, and you'll find after a little bit of algebra, it looks like this, where A is some constant. So if Russell-Long's conditions hold, if that's 0, you get the desired result. So this is kind of good. Moreover, let's go back to terms of trade. Let's consider Nash bargaining, just following up on Maliko. You know, in Maliko, you maximize the Nash product. Here's the surplus of the buyer. Here's the surplus of the seller. But look, because W is linear, the surplus of the buyer is just U of Q minus phi D, and the surplus of the seller is phi D minus C of Q. So it's basically a static bargaining problem, because the entire future value of acquiring more wealth, in this case, more cash, is totally summarized by what's that going to do to your centralized market value function. And in particular, following up on I think it was Derek's question, I forget who asked it, anyway, you don't need to know the money holdings of the counterparty because they don't even enter the Nash problem. Well, with one exception, the seller's money holdings do not enter the, so you don't need to know Walmart's, portfolio. Their marginal value of money is just phi. It's value in terms of numeraire in the centralized market. You don't even need to know the buyer's money holdings in the Nash product, except you have this constraint. This constraint says you cannot actually turn over something in excess of what you have. So the buyer's money holdings do not enter the Nash product, but they enter the constraint. But anyway, so first, the Maliko model was a little bit hard. The Bellman equation wasn't too bad, but it had this bargaining, which was a little problematic, especially if we have private information about asset holdings. And then we had this distribution. So we've tamed the distribution because of the history independence, and we've tamed the bargaining problem, making it very easy. By the way, once you see how these models work, Per Kusal gave me this suggestion. You can call them modular. You can swap out Nash bargaining for, say, Kalai bargaining or Rubinstein bargaining. You can swap it out for Walrasian pricing if you want. And that's not crazy because you can reinterpret the decentralized market as multilateral meetings. I mean, Walrasian pricing is always crazy, but it's less crazy if you have multilateral trade than if you have bilateral trade. You can certainly swap out this Nash bargaining for a price posting, and there's lots of papers on that. So it's kind of interesting. Similarly, you can swap out in the decentralized market this random matching assumption with directed search. And there's all kind of other things. You can take pieces in or out of this model. And shockingly, it's very, very simple to use. I don't know if people teach overlapping generations models anymore. If you've ever seen one, they're actually pretty easy. The reason is they take an infinite horizon dynamic general equilibrium model and it reduces to basically a sequence of 2 period problems because each generation is assumed to live 2 periods. So in that model, after you spend your money, you die. Here you don't, you go to the centralized market and re-optimize your portfolio. But it still ends up looking like a sequence of 2 period problems. I know I'm going a little bit fast, but I want to cover a lot of material. Here's another lemma. This constraint binds on the equilibrium path, except for one exceptional case, which I will talk about later. And people either see this immediately or fail to understand it completely. The somewhat subtle aspect. It doesn't mean if you find yourself in a bar with $1 million, you're going to spend all your money. No. It means if you're going to only spend $20 at the bar, don't bring $1 million when you go out. If you're only going to spend $20, you should bring $20. Because then you could have saved on the labor supply or had more consumption in the last centralized market. Now you might say, yeah, but now you have cash left over. Well, the intuition is cash is not a good savings vehicle. It doesn't pay interest. And if there's any inflation, it actually has a negative real return. The one exceptional case, if you run deflation at its can't think of the word, it's minimal level. If you set your policy can control the inflation rate and run what's called the Friedman rule, which minimizes inflation by having deflation, you get an exceptional case, but I'm not going to talk about that right now. So the general idea here is since these assets are valued for their liquidity, you're only going to bring the amount of the asset that you want to spend. Any questions? Okay. Now, by the way, the other question is why doesn't the distribution of money holdings enter the value function? Well, it does again implicitly. It's in the notation, but it's implicit in the notation. I could make it explicit, but in fact, I don't really need to because here it's going to be degenerate. So this is just so much easier. And it still captures all the essential ingredients like, specialization, credit is difficult due to lack of commitment, and record keeping or monitoring. You can, of course, do this with perfect credit. It's kind of easy, and it's well worth doing. You should do it as an exercise. And you would see that you get the first best if there's perfect credit. In general, you're not going to get the first best here. Okay, that's the model.
Right.
Yes.
This account seems very particular for this case that there is no uncertainty, the result that the money hold doesn't bind, right?
Right. I can speak to that. So in fact, we know sometimes it doesn't bind. If you end up being a seller and not a buyer, it doesn't bind. So there is some uncertainty. It's the uncertainty whether or not you're going to actually find yourself in a situation where you need liquidity. That's the uncertainty. You could even generalize that to say you meet many different types of people. Some of their goods you really like, and some of them you like just a little bit. So, the case where you're a seller here, you don't like their good at all. You can say you like some goods a little bit. So the generalization of the lemma is you have to spend all your money with positive probability, not necessarily with probability 1. So in the most favorable situation, when you really have a demand for the product of your counterparty, then you should spend all your money. If you find yourself in a meeting where you don't like the other person's good You might not spend any money, so of course it's not binding. If you like it a little bit, you might spend some money, but not all your money. So it's still not binding. But it has to be binding with positive probability. If not, just rerun my proof. You could have brought less money and been better off, using the result that currency is not a good savings vehicle. Oh, so I said here we're using Nash bargaining, but to speak to this issue about this module aspect of it, if you solve the Nash bargaining problem, look at it, plug in the constraint by the lemma to eliminate, so D equals M. Now it's a one-dimensional optimization problem. You're going to choose Q, and the solution looks like this, which is kind of messy, but it's the same actual solution we had in the second generation models with divisible goods, but indivisible money when you use Nash. The difference is in the earlier model, the buyer just transferred one unit of currency, or more generally assets. Here, the buyer could transfer any amount of money in some interval. Of course, in equilibrium, he spends all his money. He goes up to the limit, D equals M. But the key difference here is M is an endogenous choice back in the centralized market. So this is just an example with Nash bargaining. That's the, when I wrote down the Nash maximization problem, here's actually the solution. You can actually solve it out. The solution's here. So let Z denote real balances. It's cash, but denominated in terms of numeraire, because phi is the relative price of cash in terms of this numeraire consumption good. So the real balances you're going to transfer to the seller, well, it's this generic bargaining solution that I think I called it last time. If you want Q, you have to transfer V of Q to the seller. Now, this modular aspect is, if you got rid of Nash, you can put in Collide bargaining. The formula is much easier. And as I think I mentioned last time, these days I usually just use this generic mechanism, which captures Nash, Collide, and many other bargaining solutions. It also captures Walrasian pricing, imperfectly competitive pricing, and many other things. The only properties I need is that if you don't get any stuff, you're not going to pay anything. If you want more stuff, you got to pay more. Because many of the results one can derive in this class of models do not depend on how the terms of trade are determined, as long as it has the natural assumptions. I'm going to show you a picture. Here's how it works. So utility in blue, cost in red. I showed you a version of this picture last time. A generic mechanism is just some way of splitting the terms of trade. So, individual rationality says the payment you make has to be less than the utility you receive. Otherwise, you're not going to buy the stuff. And for the seller, the payment you receive has to be greater than the cost of production, or you're not going to do the deal. So this green curve is some abstract representation of some mechanism. As I say, Nash and Collide and Walrasian pricing are all special cases. The Walrasian pricing case is going to be linear. And so the way that decentralized market trade works is, well, here's the money holdings I have, which in the meeting are fixed or predetermined. And then I go to the green curve, this generic bargaining solution, and it tells me the quantity I'm going to get. And one could, in general, prove the quantity is less than Q star, where Q star is the efficient outcome. So as I say, if you allow perfect credit here, you get a Q equal Q star in every meeting. In a monetary economy, you're going to get less than that. And here's another way to look at it. Put your real balances on this axis, your liquidity position more generally. There's going to be some amount. So there's a Q star is the efficient quantity. There's going to be some amount V of Q star, I'll call that phi M star. If you have more than that, you can afford to get the efficient quantity, Q equals Q star, and you pay some amount determined by the mechanism. If your liquidity position is tight, so you don't have enough to buy the efficient Q star, you're going to spend all your money. So D of M equals M. That's why this is a 45-degree line in green. and you're going to get some quantity less than Q star determined by the mechanism. So to me, it's like 100% natural. And once again, you do not need to know the money holdings of your counterparty to implement these trades. Okay, so what do we have? Yeah, go ahead.
For the when the bargaining isn't really the focus of your paper or your research question, you don't really need to specify, right? And you can just leave it in terms of like anything that's feasible, like the V of Q.
Yeah.
Okay, got it.
By who, Cannon, and Wallace in the JP talks about constructing V. They don't use the V notation. They construct a mechanism to get the most efficient possible outcomes. Now, having said that, when you take this to the data, you have to specify V, just like you got to specify U and C, right? So when you calibrate or estimate it, then you got to take a stand. But for proving theorems, you can use this generic V.
Thank you.
Okay, so what are we after? We're after actually the demand for money, but more generally, we're after the optimal portfolio of households or firms or financial institutions. Go back to this centralized market problem. We do the next slide. Where is it? There's this first order condition. The marginal cost of liquidity equals the discounted marginal benefit of taking that liquidity position to the next centralized market. And I keep emphasizing liquidity because you can do this for assets other than currency or for multiple asset models, which is kind of the frontier of the research program. So this is your demand for money, or more generally your portfolio demand, but we need to know V prime, right? We need to know the marginal value of liquidity. So we've worked out V, uppercase V, but we haven't worked out, here it is, I'll show you. This is the same formula as in Maliko, but boy, it's a lot easier, right? Because you don't need to take the expectation with respect to the counterparty type, because everybody has the same amount of money. And the bargaining is basically static. So here it is. You might not trade, so you just take your liquidity position or your portfolio to the next centralized market. If you find yourself in a position where you want to buy something, well, you're going to get U of Q of M. The Q of M is what comes out of your bargaining or price taking or price posting, whatever modulo you want to stick in for determining terms of trade. And how much you pay is V of Q of M. So that's your surplus. It's very simple. Remember, it comes from the fact that the first lemma has the continuation value linear. So the surplus, as I say, is essentially static. When you're a buyer, your surplus depends on your money holdings. When you're a seller, it doesn't. We have established that. It depends on the money holdings of the counterparty, but that's degenerate. Everybody's holding M equal to uppercase M. So this is, a super simple value function, and it allows us to make a lot of progress quite tractably. I take the derivative. Remember, we want to have V prime, so we can put that into the money demand equation. So here it is. V prime is W prime from the first term. Alpha 1 times, U prime Q times Q prime M, which I factored out, minus V prime Q, Q prime M, which I factored out. Your own individual M, lowercase m, does not enter the third term, so the derivative is 0 in the third term. So this is your marginal value of money, and you can see how it works. You might not spend it in the decentralized market, so you just carry that money forward, which is not a happy scenario because cash is not a good savings vehicle. But if you find yourself in a position where you need liquidity, which occurs with probability alpha 1, well, this is how much more utility you get from the trade. You get to consume more, but you have to actually pay more. And Q prime tells you how much more stuff you get if you have more liquidity. Okay, good. The rest, it's all very simple, one step at a time. Each step is simple. We're making good progress. We've already established W prime equals phi, that's the linearity of the centralized market value function. Now I use this bargaining condition here with lemma 2, that you're going to spend all your money in this meeting. I take the derivative and I get fit over here, implicitly differentiating this, I get the derivative of q with respect to m is phi over v prime. So here's basically how this value function v prime tells you how much your payoff increases with having more liquidity. This tells you how much you get to buy at the margin if you have more liquidity. If q is bigger than q star, it's not binding, so having more money doesn't help. You're already satiated in liquidity because you can get the efficient quantity, and it's easy to see nobody ever wants to buy more than that. I mean, you'd love to have more than that, but when you and the seller are negotiating, it's not worth it to have a quantity where the marginal cost is above marginal utility. If your liquidity position is binding, so you're forced to consume q less than q star, but this is basically how much more stuff you get if you have more cash. If it were Walrasian pricing, then actually V of Q is just the Walrasian price times Q. So then V prime is just the price. But, you know, I don't want to restrict attention to linear pricing because it's extremely special and it actually matters a lot for policy, as you'll soon see. So we have all the ingredients. In this equation, V prime, I plugged in W prime equals phi. This term I leave alone, and Q prime we just worked out as phi over V prime. And then just for elegance, I rewrote it as phi times 1 plus alpha lambda of Q, where lambda of Q is this thing here. And early papers used lambda because it stood for liquidity. It's how much more you value the asset than you would value it if it was simply a store of value. It turns out, just by dumb luck, this liquidity premium is equal to the Lagrange multiplier on this constraint. So using lambda was a good choice, right? So I like to write it that way, just because, you know, writing u prime of q over v prime of q minus 1 is kind of messy. Just use lambda. And of course, when the constraint's not binding, the Lagrange multiplier is 0. So if you know anything about dynamic programming, which I hope you do, you just now proceed using standard routine methods. You substitute into this Walrasian. This should have a beta here. This is the first order condition from your choice of, in general, a portfolio. Here, your choice of currency needs a beta. Now you plug in the V prime, and that's what you get. In dynamic programming, this last step, to get what's called the Euler equation, you got to be careful with timing. You see, it's cost of liquidity in this centralized market, and it should be the discounted, so the beta is missing, marginal value, and the value depends on the Q next period and the phi next period. So this is your Euler equation. And now we're in some sense done. This describes the demand for Q, taking as given the prices. That is to say, in the centralized market, there's going to be some relative price of currency in terms of numeraire. You need to know the whole sequence of prices, of course, because it's a dynamic problem. But it's written here as a first order difference equation, so kind of convenient. At any point in time, you're going to have some demand for Q, taking the price sequence in the centralized market as given, and it's going to satisfy this equation. You might say, well, that's demand for Q. What about demand for money? Yeah, well, the money demand comes from this bargaining or whatever the mechanism is solution. So once you know the Q path, taken as given the centralized market prices, you know the M path. So from a decision theoretic point of view, that's your final answer. One little detail, you may remember this from studying dynamic programming. There's also implicitly in the problem some transversality condition that the Q path you choose has to be bounded. in a particular way. I'm not going to get into that. It's a technical detail, but it's important. I will mention it again in a little while. Any questions on the Euler equation? If you did say money in the utility function or some other reduced form approach, you'd also get an Euler equation. I mean, the mathematics is going to generate an outcome like this, whether you have good economics or not. So these kind of Euler equations appear everywhere: overlapping generations, models, cash in advance. The difference is this has some claim to microfoundations. Embodied in the analysis is the search and matching problem, limited commitment, and complications in terms of record keeping or monitoring. Then it allows for much more general pricing than simply Walrasian. So it's it has interesting economic ingredients, but any monetary model is going to generate an Euler equation, something like that. What I did in the next slide is the following. This is the decision theoretic solution. It tells you your choice of Q, or equivalently M, taking as given prices. Now let's use market clearing. So what I'm going to do is I'm going to eliminate Q from this equation using the bargaining solution. So I want to really write it in terms of M, not Q. And then I'm going to use market clearing. I'm going to set little m equal to big M. Just to repeat what I said. So this bargaining solution, I'm going to get rid of Q because Q is just equal to V inverse of phi M. So lambda of Q is lambda, this is composite, lambda composite V inverse of phi M. Then I said little m equal to big M, that's market clearing. Now I've eliminated the quantity little m. I mean, I've replaced it by big M, but that's exogenous, that's a policy variable. And now we have what's called the asset pricing equation, which if you take in any finance, you see asset pricing equations all the time. I mean, that's kind of all you see. This is a standard asset pricing equation, except for two things. One, usually you see the marginal rate of substitution out here, right? U prime at C T plus 1 divided by U prime C. Yeah, it's there, but actually, if you look at the special utility function here, where did I have it? Here. Well, you can see from here, U prime equals 1 in equilibrium because of the special utility function. So there really is a marginal rate of substitution out front. And the second difference is standard asset pricing equations do not have the liquidity in there. This one does. So that's why finance has it all wrong. Agreed? If you use standard finance to price this fiat currency, the only equilibrium is the price of fiat currency must be 0, because this will raise the markets and there's no liquidity premium in there. And that's just like saying in Walrasian equilibrium money cannot be valued. But that's because standard finance misses the liquidity component. And I'll come back to that in a few minutes. So let me just define an equilibrium. An equilibrium is simply a solution to this equation in terms of the price sequence phi. Given phi and the exogenous policy choice little m equals big M, we know the Q's. Going back to the centralized market, we know U prime X equals 1. I just talked about that. You find labor supply from the individual budget equations. So once you know the price sequence, the asset price sequence, you know the entire general equilibrium. One interesting thing to consider is stationary equilibria. And one way to do that is to assume the exogenous M is constant, right? You typically wouldn't, so you want to have everything constant in terms of fundamentals like beta and alpha and the V and the U and the C. You want real factors to be constant to get a stationary equilibrium. For fiat money, we can do one better. It's possible to allow the money supply to grow, say at rate mu. We could define a stationary equilibrium as to be an equilibrium where real balances are constant. So remember, Z equals phi times M. If the money supply grows at rate mu and the price level grows at rate mu, real balances will be constant. So that's useful because we can talk about stationary equilibrium, but still have monetary policy in the model explicitly here as the choice of a path for the money supply. Now, if you've ever worked at a central bank or been exposed to people who have, you might say, usually these days they set policy at central banks by interest rate rules, not money supply rules. That's true. It turns out to be equivalent, as I'll show you soon. But anyway, if I take this difference equation and use Z equals phi times M, and I replace M next period with 1 plus mu this period, you get this beautiful equation, which is it's an asset pricing equation, but it's in terms of real balances instead of prices. And it's kind of beautiful for lots of reasons. One is in stationary equilibrium where Z is constant, I can cancel the Z's from both sides, and then this gets real easy. I know I'm going fast, but you're not slowing me down, so I'm going to keep going. Maybe I'm going so fast, it's hard to think of questions. I prefer to think I'm explaining it so beautifully, there's nothing to ask. It's all perfectly clear.
Can I was not supposed to be the one asking, but this equation you mentioned, like the finance get wrong, like this is something that we discussed about bubbles.
This equation here?
Sorry?
Which equation? This one?
The first one, I think is the same. One would be real balance. You do have a non-zero solution that would be an explosive path, right? So that would be, so that's this is like you, I don't know, like maybe it's just interpretation, but like one would say that the explosive path is a bubble.
So a couple of things. I have it here somewhere, a long way away. Okay, I've got all the bubble stuff here, but it's a long number of slides away, so I won't get there. So I'll talk about it.
I'll wait.
No, I'll talk about it. I can't find my place.
And just to add to this question, like the distinction between this liquidity term and what finance people call like convenience premia or convenience yield would be helpful, because I know you on that earlier.
Convenience yield, right. So they want assets to be valued above their fundamental. And I talked to Anna Fissing-Jorgensen over dinner and explained this whole thing to her. She totally understood it, but couldn't be bothered in her models or papers to use it. So they have something called convenience yield. The natural interpretation there is you put the asset right into the utility function. They're typically not talking about currency, they tend to talk about T-bills. And that's basically the same thing, because you can swap T-bills for currency relatively easily. Not quite as easily as you can swap demand deposits for currency. You know, there you just need your ATM card, but relatively easily. So they wanted to have a value in this asset pricing equation here in excess of its rate of return. Why? Because, you know, T-bills have a lower rate of return than corporate bonds. So they're going to say T-bills must have something else. In this setup, we would say currency must have something else. So they give it utility. Now, they don't want to call it utility, so they call it convenience. They get the same equation, except we can interpret what this thing is. The convenience is having more of the asset in events which occur with probability alpha 1, relax your constraint on the transactions you make. That's going to give you some additional Q, this object you're buying, which could be a good, could be a factor of production, could be an asset. And how much is that worth to you? That's the utility of using this object Q, either for consumption or production. And it's going to depend on things like the mechanism for determining the terms of trade. So when they have convenience, you know, they have to assume a functional form for convenience. And here that emerges as an outcome of these deeper specifications, deeper features of the specification, including, you know, the search, the matching, the terms of trade, and everything else. So they call it convenience, and I call it liquidity. But both approaches are meant to add a term into the asset pricing equation so that it can have a return higher than its fundamental. I mean, I think I'd be embarrassed if I was doing convenience yield in finance. I'm jealous of those people for being so successful, but it's kind of embarrassing. Suppose in finance, I asked you, why is General Motors stock trading above IBM stock? You're going to say, it's more convenient. That wouldn't be a very satisfactory answer, right? So to say that corporate bonds have a higher rate of return than T-bills, if that's supposed to be a puzzle, the solution has to be something more interesting than T-bills are more convenient. Even though it rings true, they are more convenient. This is precisely a model of that. So the convenience yield thing used in this empirical finance work, great work by all these good people, but this is the micro foundation for what they call convenience yield. You like that answer?
I mean, so I think it's a nice answer in terms of like when you're thinking about what could influence convenience yield, it's good to kind of think about these exact frictions. I'm a little bit wondering if there's like a sufficient statistics argument that is kind of like, look, like at some point, the thing you really want to know is D convenience yield, D quantity, or something like that. And
the Lucas critique, right? You know the Lucas critique? Good.
Sure.
This exogenous functional form for convenience is not going to be invariant to policy interventions. Where there's some hope, the search, matching, bargaining, frictions, might be invariant. Maybe not, because those could be endogenized too. But if you want to see how the equilibrium is going to change after a policy intervention, it's just standard Lucas critique that you can't do that if you assume a reduced form like money in the utility function, which is just another label for convenience yield. So that's the reason you want to go deeper to do empirical and policy work. I mean, in addition to theoretical elegance and trying to get more understanding of this so-called convenience yield.
Can I just comment one thing as like a practical example of the problem of just using convenience yield? So there is a paper, a working paper right now. It's called the U.S. Public Debt Puzzle. Some of you may know. And one of the conclusions is that it's possible that they find that the U.S. debt is valued way more than what should be based on the future values of revenues, of government revenues. And one of possible explanations they highlight is the convenience yield. The problem is that if you don't have a micro foundation for what the convenience yield is going to be, from the point of view of policymakers, it's a problem, right? Like convenience yields could disappear 6 months from now, and then the U.S. just had to default the debt because they are not able to generate enough tax revenues to pay back that. Right. So if you cannot model why you're having this convenience yield, then have a good theory of why it exists and why it should keep existing in the future or not, it is a problem. We cannot just like, maybe for an asset price perspective in the short run, if you're going to do some strategy on an investment bank on some arbitrage and make some money, that's sufficient statistics enough. But depends on the big problem.
Let me say that for the discussion after that, because time is getting scarce. I'll add quickly. So convenience yield is just money or assets in the utility function. So what should be in the utility function in America? US dollars? What about Canadian dollars? What about Bitcoin? What about central bank digital currency, etc.? This is related. Should it be T-bills or US debt more generally? All these things come up. You might need micro foundations. I want to show you an explicit case study. And we can talk about these generalities more. Let me answer Bruno's earlier question. This is a difference equation. So set mu to be constant. It's a difference equation in Z. Solutions are equilibria. Yeah, they look bubbly. However, in other words, there's lots of solutions to this. I'll tell you about them. But they can't be unbounded because that would violate the transversality condition. I want to come back to that in a couple of minutes. First, I want to talk about stationary equilibria. Here's this difference equation. I use uppercase phi. as I alluded to, if Z is constant, you can cancel here and I can solve for this. So this is in any stationary equilibria, here is, it's one equation or one unknown. It gives you Z, liquidity. It's going to depend on monetary policy, the money growth rate. And in fact, I want to rewrite it because of what I said before. Central banks usually talk about interest rate rules the last couple of decades. They used to talk about inflation targeting or money supply targeting. Let me define an interest rate. So you can price any asset in the model, even if the asset's not traded in equilibrium. Let me define a real interest rate by asking agents how much numeraire they give up in the next CM for a unit of numeraire in this CM. R will be the answer. And you know, it'll be in stationary equilibrium, 1 plus R equals 1 over beta. That's their marginal rate of substitution when X is constant. Let me ask about it. We define a nominal interest rate, 1 plus I, by asking how many dollars you'd give up in the next centralized market to get $1 today. Define that as the nominal interest rate. And then you probably heard of the Fisher equation. You should have. It's the only thing you should remember from most macro courses you've taken, although even it's wrong. But there's no arbitrage conditions. 1 plus the nominal rate, the answer to this question, will equal 1 plus pi, where pi is inflation, times 1 plus R. This is a no arbitrage condition. So let me put two pieces together using the Fisher equation. In stationary equilibrium, by definition, inflation equals the money growth rate. So I got 1 plus mu here times 1 plus R, that's 1 over beta, okay? So I could replace in my steady state condition here, I could eliminate mu equals pi and then get rid of pi using the Fisher equation, and I get this. This is the solution to the problem. This is not it. Where am I? Wrong page. Here it is. Okay, so this equation here, in terms of L, if you do your arithmetic, it's very easy to reduce this to L of Z, the marginal value of liquidity. If you want to call it a convenience yield, you people out at Stanford, keep calling it that. I like to call it the liquidity premium. The probability you're going to need the convenience or liquidity of the asset times L equals the nominal interest rate. So once the central bank pegs the nominal interest rate, that pins down the stationary equilibrium. I already mentioned this. It looks like very, very simple. It is simple, but don't forget the search and matching problems, the preferences and the mechanism, you know, are involved in this, and behind it all is these frictions. But I mean, you couldn't ask for, the model seems complicated, right? It nests general equilibrium theory, including real business cycle theory and search theory. It has all these frictions that allows for generic pricing. It has assets being valued for their liquidity, and yet you get something quite interesting. There's existence and uniqueness results all over the place. I'm going to skip a lot of the stuff to get to something. But the uniqueness proof is non-trivial. I have it here. Policy. It's easy to see, it's not so easy to see. One can prove that higher nominal interest rates reduce the demand for liquidity. Effectively, I is the cost of liquidity in terms of currency. In Vissing-Jorgensen and Krishnamurthy, it'll be the spread between a corporate bond and a T-bill. Here is the spread between currency, because it's the only liquid asset in our little example here. And this interest rate I defined in terms of the thought experiment, phi, it's still a spread. Here's some results. And this is an example where, you know, the policy implications depend on the details. So there's two frictions going on here. One is if the nominal interest rate is positive, that's a wedge because you're making liquidity costly to hold. And Milton Friedman figured this out, you know, half a century ago without having a model. Set that to 0. You should get rid of that. It's like a tax on liquidity. because the currency you're using is not appreciating fast enough because of inflation. If you deflate at the rate of time preference, you get a nominal interest rate of 0. And with collide bargaining, that gives you the efficient outcome. With Nash bargaining, it doesn't unless the buyer has all the bargaining power. So the microfoundations, what goes into money in the utility function or cash in advance or convenience yield, depends on details. And the reason with Nash bargaining, even at the Friedman rule, I equals 0, you get inefficiency, is something called the holdup problem. If you know IO, you'll recognize this problem. Suppose I'm going to buy some machine and start a business and then hire you to work for me. I'm going to tell you I have to pay you a low wage. I have to cover the cost of the machine. You're going to say that's a sunk cost. You have to pay it whether you hire me or not. So you can't recoup the sunk cost in the bargaining. Well, being a good economist, I anticipated this, and hence I'm going to underinvest in capital. That's what goes on here too. In the decentralized market, the buyer who facilitated the trade, it's his money holdings or his liquidity which facilitate the transaction. He's going to say, I want a large Q. I want to be able to recoup my cost of being liquid. I brought this liquidity to the market. And the seller is going to say that's a sunk cost. It shouldn't affect the bargaining. You're going to know this ex ante because you're a good economist, so you bring less liquidity. So the microfoundations of how the asset actually conveys value matter a lot. Even at the optimal policy, you're going to get inefficiency if this non-Walrasian pricing rears its head. And indeed, not only does bargaining matter, it matters which bargaining solution you use. Go pretty fast now. I want to show you some numbers because you've been asking about does this matter for things using microfoundations. Here's the classic question of monetary policy. What's the cost of inflation? So here's Milton Friedman's intuition in a diagram. The blue curve would be, say, Nash bargaining with theta equal 1. And it's gonna resemble a money in the utility function model or cash in advance. At I equals 0, the Friedman rule, you get the first best. So welfare is maximized there. And what do we know about maximum? Well, by the envelope theorem, a small deviation has only a second order payoff impact, right? If you're at the maximum and you move a little bit away, you don't lose much. So this means that moderate inflation has basically no welfare implications. In standard theory, money in the utility function, cash in advance, etc. I'll take the model we've been studying today, have Nash bargaining with theta less than 1. Well, I equals 0 is still the optimal policy, but it's a corner solution. I equals 0, you can't, there's a 0 lower bound problem here. You can't drive the interest rate below 0 because it would set up arbitrage opportunities. So it wouldn't be in equilibrium. So it's still the optimal policy, but it's a corner solution. You see, welfare is steep at the optimal policy. That means the envelope theorem doesn't apply. It's a corner solution. So now a moderate inflation has a huge welfare impact. That's to say first order. So in theory, it's easy to see that as you put different microfoundations into the model, it's going to dramatically change policy implications. And let me just calibrate it up quickly. I'm going to choose this utility function. It's the one usually used in this literature for the decentralized market trade. It's constant relative risk aversion with this B parameter stuck in there to force U equals 0. I'll use a linear cost of production for centralized market goods. I'll just use log X. I'm going to do the simplest version. You can make this as fancy as you want. What parameters do we need to calibrate? Beta. I'll set that to match my favorite real interest rate. These parameters, big A and little a of the decentralized market utility function, I'm going to estimate or calibrate to match money demand, which is this picture here. Real balances against the nominal interest rate. That's kind of all the parameters I need. I need to know the search and matching frictions, but they're a little bit hard to calibrate, so I'll just try different values of them. One can be more ambitious there. The remaining parameter to calibrate is this Nash bargaining power. I'm going to pick that to match retail markups. So this is not the only application or interpretation, but you can think of this model as a model of retail. And we have excellent data on retail markups. I can go into detail now, but I don't have time. And I calibrate that. And it's the natural parameter, right? The bargaining power of the buyer, if that's high, it's going to give a low markup in theory. If the bargaining power of the buyer is low, the markup's going to be high. And so when I get markup data, that pins down bargaining power. And now I'll ask the classic question in traditional monetary economics: what's the welfare cost of inflation? I'll say, for example, suppose we're at 10% inflation. How much would you be willing to pay to go to the Friedman rule? And I'll do it as a percentage of consumption. I don't know if the convenience yield crowd has done this, but there's hundreds, literally hundreds of papers with money in the utility function or cash and advanced models. They get 0.5% of consumption is how much you'd be willing to pay to get rid of inflation of 10%. And it's for years they puzzled over why the number was so small. You're probably too young, you don't remember the 70s, but people don't like inflation. Maybe you come from Latin America, people hate inflation. And the big puzzle is it's only worth half of 1%. It's the envelope theorem, no puzzle. Now do it with theta calibrated to match retail markup, what do you get? You get 10 times bigger. And 5% of consumption is a lot. It's pretty hard to find any macro policy which is going to give you that big a welfare effect. So bottom line is microfoundations matter, not just for theoretical elegance. They matter for quantitative policy issues. I know I went really fast today, but I wanted to cover a lot.
Is that 5% the upper range? Because you set alpha sigma arbitrarily, right?
But can you repeat the question?
Is that 5% the upper range? Because you set alpha sigma arbitrarily?
Oh, not really, no. Turns out it doesn't matter very much. There's a bit of identification problem. There's more parameters than you need. So at the end of the day, if you change alpha sigma to match the markup, you'll get a different theta and it kind of washes out to be the same. So no, this is not, I'm not picking alpha sigma to maximize the dramatic effect here. In fact, it's actually bigger than 5%, but I like to use 0.5 and 5.0 because you'll never forget that, right? People have redone it with different, obviously with Collide, it's going to be different. It depends on if you have entry or not, but people in a decentralized market. It depends on people who've done private information versions. You can get that even higher. So this is not biased upward for a dramatic effect. This is like a benchmark case. It does depend a lot on bargaining, obviously. If you switch this for directed search with price posting instead of random search with bargaining, the number comes down a fair amount. The latest, I think my last publication in Review of Economic Studies with Zach Bethune and Michael Choi, we said in reality, there's some combination of bargaining and posting in retail markets. We'll let the data speak to inform us about bargaining versus posting, and then we get some number, it comes down a bit from 5, but we also check all the details about how you do free entry and how you do many, many different things. So this is still an ongoing research program. You might think it's not of critical importance these days because inflation is low and stable. This says it better stay that way. Okay, I don't have much time, but I'm going to just talk a little bit more. Yeah. I have a short course on how to do nonlinear dynamics, very short, 2 slides. But that difference equation, I could plot it in, this is any x, ours happens to be real balance. So I plot the difference equation, and there's going to, with fiat currencies, there'd be two steady states, the monetary one we're focusing on and a non-monetary one at the origin. There's actually lots of other paths that are equilibria. Here's a 2 cycle. This is hearkening back to what I said last week. Any model with liquidity, if it's any good, is going to have multiple equilibria, because liquidity is to some extent a self-fulfilling prophecy. How much you want the asset for its liquidity depends on how much other people want it. And the most important thing to notice about this picture, other than, you know, the artistic flair, is this is for currency. Switch it out for a real asset like a Lucas tree. You don't lose these equilibria. For moderate risk aversion, you can get cyclical dynamics, you can get chaotic dynamics, and you can get sunspot equilibria, which are stochastic dynamics. These are all time varying bubbles, and it holds for currency, but it also holds for real assets. And the bubble is there because the liquidity premium is keeping the price of the asset above its fundamental. And because liquidity is to some extent a self-fulfilling prophecy, there's lots of equilibria. I don't have time to talk about the details. Here's a nice picture of a chaotic. There's a simulation. That's an equilibrium with all fundamentals fixed. Yeah, I want to make one point that's important. The model I showed you today was developed as a natural outgrowth of the earlier models we did last week, where people are meeting at random, you know, and going back to Jevons and Menger and Wicksell, classical, you know, economists of 150 years ago. Who you meet is random. He might be a buyer, he might be a seller. For most applications these days, that's not the way it's being done. There's going to be a class of agents who in the decentralized market are always sellers. They're like retailers, or firms providing capital, or financial institutions selling assets or providing loans. Where there's other agents who are always buyers in the decentralized market, households buying goods from retailers or producers, firms buying inputs, firms getting loans, entrepreneurs getting loans. So there's these two distinct classes. They know when they get to the decentralized market whether they're going to be a buyer or a seller, and they tailor their liquidity positions based on their roles in the decentralized market. You couldn't do this in Maliko or Kiyotaki Wright because, you know, somebody's going to be a seller in every period of the decentralized market. They're going to be accumulating assets, but there's no chance to spend them because they're never a buyer. That's fine here. That's not a problem. They can take their assets, their revenue from sales in the decentralized market and spend it in the centralized market. So having two types is actually more natural for applications. It's very much similar to Pissarides' model of search rather than Diamond's. Original Diamond just had people looking for trading partners. Pissarides had firms looking for workers, workers looking for firms. It's a two-sided market. And what makes that so interesting is you can have entry in Pissarides when firms post vacancies. So here you could do that too. What we've learned today is to get real balances, it's going to depend on the arrival rate of trading partners in the DM, which will be captured by market tightness, the buyer-seller ratio. Then you can do the free entry condition, which gives you the buyer-seller ratio as a function of real balances. Why is that? If there's more cash in the market, there's going to be more firms entering trying to sell stuff. So both of these things are upward sloping. It's another reason to get multiple steady states. And you know, most modern applications these days are not saying you might be a buyer or a seller depending on who you meet. It's that, you know, retailers sell goods and households buy goods. You know, banks lend money, entrepreneurs borrow money. So you have a deterministic role before you go to the decentralized market. There's plenty else I could teach you. This is very important because this framework is not about currency. It's about pricing assets and recognizing that liquidity matters. So this is real assets. instead of currency. It works basically the same. I've even done a nice little comparison for you. The Euler equation for the asset pricing equation for Lucas Tree looks like this. Rho is the real dividend on it. There's no real dividend on currency. So currency has a fundamental value of 0. In monetary equilibrium, the value is great. Lucas trees have a fundamental value as well. In equilibrium, where they have a liquidity rule, their value is going to be in excess of the fundamental, and there are chaotic, stochastic, and cyclic equilibria where Lucas trees price varies over time in interesting and complicated ways. Now, going back to this convenience yield nonsense, you can always match a microfounded model with a reduced form model. You see, once you know everything I've done, you get this liquidity premium L. You can start with L. Take that as your primitive. And of course, you're going to match the data, right? Just like if you derive a labor supply curve from first principles, you can start with the labor supply curve and it's observationally equivalent. Except if you change the institutions, including policy, your exogenous labor supply curve, or money in the utility function, or Lucas trees in the utility function, will likely not be invariant. And if you microfound it, you have a much better chance. You have some hope of being able to predict how it's going to change in response to policy. Here's how to price a Lucas tree with liquidity. Lagos uses this model to explain the equity premium and the risk-free premium. And that's the end of these slides, but this is only 3. I have like 6 sets of these slides. We're out of time here. You know, at Wisconsin, people are in the union, so I don't work overtime unless you pay me more. So I'm going to stop teaching. But I will stick around if you guys want to chat or ask me any questions.
Thank you, Randy. I would just want to remind everybody, we will post these slides. And so Randy offered to post the slides, is that correct?
Yes.
And we
I'll
are
send it to you. You post it, right?
Yeah, just send to me. And we also have the lectures are recorded, and we also post on our website. We are gonna send an announcement email. And if you are not, if you didn't subscribe to get the SaMMF emails, please do it. We have great seminars and lecture series and workshops. We're happy to have you follow us. Thanks.